Welcome to Beyond the Qubit. I'm your host, Frank Dekker. My guest of today is Yuval Boger, the Chief Commercial Officer of QuEra. QuEra is an interesting party to talk to because QuEra makes a quantum computer based on natural atoms, and they have very exciting partnerships with MIT and Harvard. So thank you for being here, Yuval. I'm excited. Yeah. Maybe let's start with can you give us a short introduction of your journey in quantum technology? What sparked your first interest and how did you arrive at your role today?
Well, thank you for the opportunity to be here, Frank. I have been in quantum for about 5 years now. Historically, I have always been attracted to frontier technologies, whether it's wireless power, virtual reality, or other things. By way of education, I have both a graduate degree in physics as well as a graduate degree of business. So it was always interesting for me to do things that have a deep scientific background. I started my quantum journey at Classic, an Israeli software company that makes a software platform that allows you to quickly encode complex algorithms into multiple hardware platforms. And then after a couple of years, I transitioned to the dark side, to QuEra, which makes hardware. And I think anyone listening to this understands that quantum is such a fascinating technology with such amazing potential, but also at a very, very early stage that leaves a lot of open questions and a lot of opportunities to do interesting things. One of the unserious tests that I usually do before entering a new field is check the Twitter, now X handles. When I was starting a virtual reality company many years ago, the Twitter handle VR Guy was available. And then when I was working at a wireless power company, Charge Guy was available. And when I was considering entering quantum, Qubit Guy was available. So I'm on Twitter, I'm Qubit Guy. And also the superposition guy. And although by itself that's not important, it's a sign of a very early stage industry where some of these amazing handles are not yet taken.
Okay, that sounds great. What sparked your, maybe why did you move from classic to the dark side, as you call it? And why do you call it the dark side?
No, I'm joking. It's not really the dark side. I think that software is wonderful, but software is not going to be useful without hardware. If you can have an operating system or an amazing application, but there's no strong enough CPU or GPU to run it, then it's just a theoretical exercise. So in an early stage market, I felt that hardware precedes software. And therefore, it made more sense for me to work at a hardware company.
Okay, then that's clear. Thank you. You have had multiple roles at Next Gen Venture Partners, Classic and QuEra, and you had multiple podcasts. What lessons from those experiences do you carry over, and how did they shape you?
So before QuEra and Classic, I was CEO of several companies, usually not at the same time. Several CEO of companies in various fields, in various high-tech fields. And podcasting was always a good way for me to both educate myself and my listeners on the market. So I used to do a virtual reality podcast and a wireless power podcast and other podcasts. And also to engage in the market and have deeper conversation with executives and people who are interesting or important or both in the market. I started my professional career as a product manager. And a good product manager, in my opinion, likes to understand not what the customers need, but what they will need in 18 months. So try to get into your customer's head and say, okay, well, I understand what you're saying right now. Why are you saying that? Why do you want this and that capability? And what is it going to do for you? Sometimes we start asking a question by, where would you like to be in 18 months? And what's stopping you? Why are you not there already? And I think that became a way of life, a way of professional life, sort of trying to think ahead on what customers will want, what the market will want, where the market is going, and then try to create products and service offerings that meet that requirement. I've always worked at smaller companies. I mean, QuEra today is over 100 people. I've ran similar sized companies as well, but I've never worked in a company with 100,000 employees or 50,000 team members. And I've learned that one important strategic advantage of the smaller companies is the distance from understanding a customer need to acting on it is much smaller. Sometimes you can say, I heard this last week in a trade show, I now understand something that I didn't understand before, and this is what we're going to do immediately. It's much easier to experiment with new things in a smaller company. It's much easier to get things done when you don't work in a battleship that takes many hours to turn around. The other thing I've learned both at QuEra and Classic and in previous experiences is that customers are sometimes shy. And what I mean by that is that they either are shy to ask questions, they don't know if they'll get the right answer, they don't know if they'll get an answer at all. They sometimes like to hide. And what that means is that if someone asks you a question, it is often the case that 100 other customers are also interested in the answer to that question. And therefore, being able to communicate, sometimes it's writing an application note, sometimes it's saying, oh, this worked with this particular customer, with this particular opportunity, with this particular need. Let's experiment to see how many others have the same requirements. So these are some of the things that I've learned and sort of guide me in my day-to-day work at QuEra.
Thank you for sharing that. Very insightful. And I think what you mentioned on the speed of execution, what I also sometimes feel is in my job as analyzing listed equity, and also in my firm, in my normal role, there's a lot of functional separation. So one person doing risk management, one person doing legal, one person, and all those functions optimize for themselves. But if you minimize all the risks, the risk is that you no longer take risk. And that is a worry, I think. And on your fundamental beliefs, how are they shaped? And do you have 3 bottom-up examples of experiences that shaped you in your life? And that could be things from your youth, mistakes you have seen during your career, or things that worked really well.
Many years ago, I did an MBA at Northwestern University, at the Kellogg School of Business in Northwestern University. And my kids asked me, well, what is the most important thing that you learned
Oh, wow.
MBA? It was a 2-year MBA. Yeah, okay, so what have you learned? And of course, I've learned many things, whether it's understanding balance sheets or creating a business plan or this, that, and the other. But I think that perhaps the single most important thing I've learned is that incentive drives behavior. Or if I take it a little bit wider, the strategy of the company should drive the structure. The structure should drive the incentive system, and the incentive system would drive the behavior of those that work in that incentive system. And so the idea is to create an alignment between what the company wants to achieve and what people actually do. And you can imagine that a lot of people do what certainly there's altruism. They think they do what's good for the company, but certainly do what's good for themselves. So when you create an incentive system that says, well, this is the type of behavior that we reward, whether financially or through recognition or something else, then you amplify that correct behavior. So for instance, many years ago, I was appointed CEO of a software company in a turnaround situation. The company was in trouble. It was close to running out of cash. It didn't have a lot of customers, but the investors believed that it does have potential, and they asked me to see what I could do about it, both to raise money and to organize the company a little bit differently. One thing that we, after meeting the employees and understanding the situation, we adjusted the incentive system so that everyone in the company, including engineers, including basically everyone, got an incentive based on customer payments. One would think that an engineer say, okay, well, why do I care about customer payments? Well, you should, right? Because company doesn't have a lot of money. And I remember it was towards the end of a quarter. We had a remote office, and an engineer calls me on my cell phone and says, how are you doing with this project with Visa, the credit card company? And I said, well, I'm glad to tell you, but why are you asking? He said, well, because if we deliver and they're happy, then they'll pay. And if they pay, I'll get a larger bonus at the end of the quarter. So that's why I care. And to tell me what is it that I need to do to help that. So sort of long story, but the short version is once you create the alignment, once the company is aligned to achieve the same goals, then the magic starts happening. Then when you have a large team or a large enough team of talented and motivated people that are all rowing in the same direction, then almost anything can happen in a good way.
Wow, that's an inspiring story. Do you have other bottom-up examples?
Sure. We spoke about the speed in which companies operate and what they can experiment. I was in a company that competed against what now I think is, it used to be HP test equipment, then it became Agilent, maybe now I think it's called something else. And we were doing communications testing, and they were very, very methodical on it. If you know the sort of 7-layer communication stack, you start with the physical layer, and then there's another layer, and there's another layer. It's almost like TCP/IP, where TCP is one layer above IP, and IP is a layer above Ethernet, and then Ethernet is a layer above the physical layer. And so they were sort of methodically going up the stack. And we said, well, that's great, but they're HP. How in the world are we, as a small company, going to be able to compete with HP? And so we said, how about we start from the top and work our way down? We're not going to worry about the lower layer testing. We're going to go all the way up to the higher layer testing and then go down. And that kind of original thinking, then of course we tested it with customers. They were all excited about it because we basically identified white space. We identified an area in the market that was not well served, and that product became super successful and actually was really the engine that drove the company to a successful IPO on NASDAQ. So again, listening to customers, looking for that white space, being very curious. Well, why are you saying that? Why are you saying that? What's behind the position that you're expressing in this discussion? I think these are traits that carry over very well almost to all industries.
Yuval, is it fair to summarize maybe that you say it's very important to listen to the customer and that you are really close to the customer, and also that you can act fast? And if the incentives are also aligned, then everybody's rowing in the same direction, and the combination of all of that can be very powerful.
Yes, I think that's absolutely correct. The only thing that I would add is, beyond listening to the customer, you have to maintain a curiosity.
Okay. Yeah.
Oh, this is interesting. What's going on here? That's one of the things that I enjoy in podcasts. In the podcast by now, the Superposition Guide podcast had close to 200 episodes, and sometimes guests ask me, well, can I get the questions in advance? And I'm saying, well, I would give them to you, but I don't have them myself. Let's just have a conversation, see where it goes. I'm curious to learn about your business. I'm curious, and I'll try to listen to what is it that you're saying, and use that to form the next question. So let's just have a conversation. So being curious, I think, is just as important as listening.
That's interesting. What I really like is that, and where you differentiated from my conversation so far, is most people cite things from the physics and from the technical. And you start with the customer and listening to the customer and customer curiosity. So I think that's an interesting observation. Maybe we can move to QuEra. Could you describe, in basic terms, from somebody outside the quantum technology world, what is QuEra?
QuEra develops, manufactures, and installs and services quantum computers based on neutral atoms. Quantum computers, as we know, are expected to change the computational landscape, to be installed alongside the CPUs and GPUs in major data centers. Quantum computers are the subject of many well-funded national quantum programs because so many nations and organizations understand that quantum is a strategic technology because of the positive and also negative impact that it could bring. And there are many different ways to build quantum computers. Quantum computers, as you know, are based on qubits, quantum bits. And so how do you create these quantum bits? Well, there are companies that use superconducting qubits, like IBM. There are companies like Quantinuum that do trapped ions. There are other companies that use photons to create qubits. Well, we used individual neutral atoms. And neutral atoms, as I'm guessing we'll get into in a little bit, have tremendous advantages in the ability to ultimately create large-scale, error-corrected computers that are key to unleashing the potential of quantum. So QuEra, based in Boston, an outgrowth of amazing work that was done at Harvard and MIT, builds computers out of neutral atoms.
And can you explain me a little bit, what are the relationships with MIT and Harvard? And why is QuEra so close to both?
4 of the founders of QuEra were professors from Harvard and MIT. 2 from Harvard, Professor Lukin and Professor, sorry about that. So two founders were from Harvard and 2 founders were from MIT. And so that was the initial connection. But 2 of these founders continue to be, both Professor Lukin and Professor Vuletic, one from Harvard, one from MIT, continue to be super active in the company, both on the board of directors and in the day-to-day operations. But it's beyond these 2 amazing individuals. We think that even the physical proximity to Harvard and MIT, just a bike ride away, is really a strategic advantage of QuEra. Because what we've shown time and again is that we can take technology, I shouldn't say take, license or use or apply technology that was developed at Harvard and MIT and very quickly turn it into a commercial product. There's a difference, there's a distance between an experiment that works in a lab, 10 minutes on a Thursday morning when the stars perfectly align, to something that can work repeatedly 100 plus hours a week. And so we were able to make that transition. Harvard and MIT is also a fantastic talent pipeline for us. We are sometimes very fortunate to be able to hire people who have graduated from Harvard and MIT. QuEra equipment is sometimes used at Harvard and MIT lab as we collaborate on experiments. And so there's really 2-way contributions. And that's why, and that's one of the reasons that we are indeed the leader in neutral atom quantum computing.
It's an interesting story. And the one thing that pops up in my head is, what about the labor cost? So, for example, I can imagine the labor cost in the US and from people who graduated at MIT and Harvard are quite expensive. For example, compared to the Netherlands, from TU Delft or something. Or
yeah.
How does that work? And especially for a startup? Or do you think, is your motto, talent is much more important than a starting salary? Or how does that work? Is it, how does it trade? I think it's a trade-off. It's not black and white, but how do you see that trade-off?
You know that in software engineering, they used to say that a fantastic or a top-notch programmer does the work of 10 average programmers, even though that person may cost only 50% more or twice as much. So one of the things that certainly attracted me to QuEra is really the amazing talent that we have. I sometimes joke that I only have a master's, only a graduate degree in physics, so they barely let me in the door, even though I was hired to run marketing. Oh, you don't have a PhD, and oh, your degree is not from Harvard or MIT, so why bother applying here? Of course, I did manage to get in the door, and of course we have many fantastic people that did not graduate from Harvard and MIT, other great institutions. But you're right. I mean, every country has an operating model in terms of cost, whether it's labor costs, social benefits. On the other hand, every country may have different structure with regards to government incentives or government grants, venture capital, as you know. So we made it work. And one reason that we're able to make it work and we're continuing to grow and grow is that based on both the scientific and commercial achievements of QuEra, we were able to recently raise $230 million, led by Google and SoftBank, and recently NVIDIA also joined. So we do have the money. I mean,
that's really an impressive stat, and I think outside the US, access to capital is much harder. And access to capital, we see it now with OpenAI. If you have access to capital, if you can deploy capital, you can make things happen. And without access to capital, it's very difficult to get things moving.
Yes, capital is important, but then other than capital, it's always good to get customer money. And that's sort of sometimes the cheapest form of capital. And QuEra was very fortunate about 3 years ago to start. I mean, the contract was signed more than 3 years ago to sign a really strategic agreement with Amazon to put our first computer, Aquila, on Amazon Web Services on the bracket. And that both gave us the credibility as well as some of the financial wherewithal to continue developing and protecting this technology. And this is expensive. I mean, software companies, one of the wonderful things about a software company is that, give or take, you just need a Mac and you're good to go, right? In hardware, we've got lasers that cost unbelievable. Real hardware costs real money, and so you need real funding to make it work.
And what is interesting is you made it work with very good strategic investors. So I think it's really impressive in combination with the relationship with MIT and Harvard. Maybe my next question, what is the mission of Q?
The mission of QuEra is to create computers that help solve classically intractable problems, that actually allow us to solve problems that have not been solved before, and do that, for the benefit of humanity. So we think that we are creating a platform that can enable both discovery and solutions that were not possible. And so this is why it's so exciting to work in QuEra and to work in quantum in general.
And what does QuEra want to achieve on a 5-year view?
Have a computer that's good enough to do that. I mean, I think one of the sometimes overlooked things about the quantum computing industry is that quantum computers today, it's just the two of us, right? No one's listening, right? Quantum computers today are useless. Quantum computers today are useless in the sense, of course, I'm saying that with a smile, but quantum computers today are useless in the sense that there's really there are very few problems that you can solve on a quantum computers that you cannot solve classically. And classical computers are cheaper, they're more accessible, they're easier to program, they're more stable, there are all these, the tools are there. All these amazing things are true for classical computers. Quantum computers today are, of course, useful.
My question is, what does QuEra wants to achieve on a 5-year view?
So we mentioned that
you want to have the computers to be better than classical computers, and currently there are not a lot of applications for a quantum computer where a quantum computer is better excels versus a classical computer.
Yeah, so quantum computers are a little bit useless right now in terms that there's not many problems that you can solve on a quantum computer that you cannot solve classically. There are some, but very few. And therefore, quantum computers are primarily used to prepare for the time where quantum computers will really be useful. And that's what we're trying to build. We're trying to build truly useful, powerful quantum computers that will allow solving these problems. Now, that means quantum computers that have enough qubits and good enough qubits. So larger and error-corrected quantum computers. Roughly speaking, let's assume we had perfect qubits, no errors. Maybe we'll talk about error correction a little bit later. But if you have fewer than 50 or 55 qubits, then you could simulate it perfectly on a supercomputer. So you don't need a quantum computer. If you only have 20 qubits, then why bother, right? Life gets interesting when you have hundreds or thousands or tens of thousands of really good qubits. Then you could solve amazing problems. So our vision in 5 years, but maybe not just in 5 years, I think it will be sooner, is to build computers that are large enough and powerful enough to solve some of the most pressing problems, whether in chemistry or material science or financial services or optimization, climate change, artificial intelligence, and so on.
That's really exciting to work on. Maybe I think we will not escape it. Let's dive into the technology. Can you explain in basic terms how the technology of QuEra works, and then especially neutral atoms?
So as we discussed briefly before, each qubit is an atom, is an individual atom. And that's great. Atoms are, by design, they're perfect. They're perfect in terms of being perfectly identical. We could take 1 billion atoms and they will all look exactly the same. There are no manufacturing inconsistencies. We don't have to worry about this atom is greener or bigger or heavier than this other atom.
And Yuval, is it correct that it is not for all quantum technologies that all the qubits are exactly, or the atoms are exactly the same? Because some use a lot of is it correct to say that some use a lot of calibration tools or control systems too?
Yeah, it is true, but I think the fundamental difference is that some qubits, like our qubits, are natural, and some qubits are manufactured. So when you make a superconducting qubit, you're basically creating a circuit, and that circuit may have inconsistencies, may have defects. Neutral atoms are perfect. And then we take these neutral atoms and we...
Can we go maybe a little bit more deeper in? So why are those atoms neutral and why are they so perfect? Could you elaborate a little bit on that?
Well, they're neutral because they're not charged, they don't have the number of protons and electrons is the same, and so they're not ions. That's a different way of creating quantum computers with trapped ions. And so they're neutral. They're not significantly impacted by electrical charge. They can be next to each other. We'll talk about how we do gates and so on. But we basically, in our case, we use rubidium atoms. Rubidium is on the left side of the periodic table, a few rows under hydrogen. And then we take these rubidium atoms and capture them in what's called laser tweezers. And so if you've seen bank robbery movies, I'm sure you have, right? You're in financial services, yeah. If you've seen bank robbery movies, there's always a scene, or there's often a scene, where the thief goes into the safe and the safe has these laser beams from all directions that trigger the alarm system. And so think about sort of an array of laser beams coming from the ceiling, and magically each of these lasers can trap a single atom. And by trapping means it creates an energy field that makes the atom want to stay really in the center of the beam. And that's super important. So first we trap these atoms in the laser beams. Then we use a combination of laser and electromagnetic fields to basically keep the atoms still, so they don't move. And there's a physical relationship between temperature and movement. So when we keep atoms still, it's really equivalent to us cooling them to almost absolute zero temperature. So this is and through this discussion, you sort of understand some of the benefits of neutral atoms. So we start with perfect atoms, so there's no calibration issues. We cool them using lasers. I know when people think about lasers, oh, I'm going to heat something with a laser. No, but in our case, we cool something with a laser. And so we don't require cryogenic cooling. If you were to Google quantum computers, it's often that you'll find these beautiful chandeliers, golden chandeliers, which are associated with cryogenic coolings. They have various cooling stages. But cryogenic cooling is a nightmare. Is a nightmare for people who want to install quantum computers because they take up a lot of space, they take up a lot of energy, they require refills of the gas used to do the cooling. So we basically have a system that operates at room temperature, that does not need this cryogenic factory. Then we spoke about the laser beams, where each laser beam captures an atom. Now, amazingly, if the laser beam moves, the atom moves with it. So all of a sudden, we have a situation where we can take any two atoms, any two qubits, and at will sort of bring them together or take them apart or take them to different places. In sort of semi-technical terms, we call this all-to-all connectivity, meaning we can bring any qubit to interact with any other qubit. And this is in contrast with approaches like superconducting qubits. Superconducting qubits basically have a printed circuit, and every qubit can only interact with nearby qubits, whether it's 2 or 4 or 5 nearby qubits. And why is that important?
One of my recent research questions at the moment, Yuval, is it possible to solve that problem, what you described, with input and output transistors? But I think if not, then for the error correction ratio, that's probably your next point.
So we can move the atoms around, and let's sort of take an example to understand why it's important. Let's assume that you and I go to a cocktail party, and I recognize you and say, "Oh, I've had this amazing conversation with Frank a couple weeks ago, and I want to go and talk to you again." If I'm a neutral atom qubit, I just walk over and say, "Hey, Frank, how are you doing? It's good to see you," and then we have a conversation. If I'm a superconducting qubit, I can't directly talk to you because you're on the other side of the room. So I have to ask the person standing next to me to relay a message to the person standing next to her, and then again and again. So it takes multiple hops until we can interact. And of course, with multiple hops, like the kids sometimes play a game of telephone, the message could be corrupted by the time it gets to you. And so the ability to move qubits around, to shuttle qubits around, allows us to create algorithms that are more efficient. They need fewer operations. Allows us to create error correction codes that cannot be done in static configuration. So really a very, very big deal. The other nice thing about neutral atoms is these atoms are, of course, they're small. An atom is very small, but we can put them to be very tightly spaced. In our system, atoms are about 4 microns, 4 millionths of a meter apart. And that means that, in something on the size of my fingernail, we could put thousands of atoms. So at least from that perspective, it's very easy to scale. Now, when we speak about scaling, that brings us to another advantage of neutral atoms. How do you create operations on neutral atom? How do you make a neutral atom change its state or interact with another qubit? Well, that works through different laser beams. So, electrons in the atom have energy levels. They can be, usually they're, say, in the ground state. They can be in excited state. And we can sort of shoot a laser at an atom and make the electron move to a higher energy state. That transition allows us to make atoms interact. So for instance, one key point in neutral atoms is what's called the Rydberg blockade. When an atom is in the ground state, the low energy state, you can think about it as being fairly small. When it's in a very high excited state, it feels like it's a huge, huge atom, very, very big. Why does that matter? Because when atoms are in the ground state and they're fairly close to each other, they're fine. They're indifferent to each other. But when they're excited, they can't both occupy the same space. So actually, Rydberg blockade means that if atoms are sufficiently close, then you cannot have two atoms in an excited state nearby. And that, if you think about sort of classical analogies, that's like an exclusive OR, XOR operator on bits, where you can say only one bit can be one, but not the other, right? And so by shooting lasers at atoms, we can make them interact. Now, a laser beam can we can shine a laser beam at multiple atoms at the same time. So we can have multiple atoms be operated on, multiple pairs of atoms. And so this parallelism also allows for more efficient algorithms for better error correction. And it also talks about...
Can you quantify a little bit what are the limits there?
What are the limits?
What are the trade-offs? So if you increase the amount of neutral atoms created by one laser, but you can also have multiple lasers, what are the trade-offs there? On performance, on energy usage, on...
Of course, there are always trade-offs in engineering. You know, if we spoke about each atom is held by a laser beam with these optical tweezers. Well, if you wanted more atoms, you'd need either more lasers or more powerful lasers. More powerful lasers are maybe a little bit more difficult to stabilize in terms of their intensity or other parameters. So you get into sort of a lot of very interesting engineering challenges on how to scale the system. But just going back to that parallel operation of being able to use a single laser to operate on multiple qubits, I go back to the superconducting qubits. A superconducting qubit, each qubit would have 2 or 3 wires, 2 or 3 controls connected to it. That sounds fine. But let's assume you need 1 million qubits. Then you're going to have what, 2 million wires, 3 million wires. That's going to be that's difficult. It's difficult to route. It's difficult to control. It takes a lot of weight and size and space, right? How do you make sure that there's no crosstalk between electrical signals on the wires? And in contrast, neutral atoms scale by just having, I'm making it a little bit simpler than it is, but just having a bigger laser. When you scale a superconducting system, the number of controls scales linearly with the number of qubits. When you make a neutral atom systems, the number of controls scales maybe logarithmically with the number of qubits. So it's much, much easier to get to larger number of qubits. And indeed, so for instance, a couple of weeks ago, a team at Caltech demonstrated 6,000 qubits on a single machine, 6,000 neutral atom qubits on a single machine. Harvard published a paper with 3,000 or so qubits on a single machine. These are numbers that you don't see yet in superconducting qubits. Superconducting qubits also create a chip. Now, if you wanted to put 10,000, 100,000 wires on qubits on a chip, well, one, it would be a large chip. But the other thing is you get into sort of impossible yield situations. How many qubits are going to be bad, and what do you do about them? And so what manufacturers typically do is they say, well, we're only going to limit the chip to a few hundred qubits, because that we can get sort of a decent balance between manufacturability, size, and yield, and so on. But how do you get to 1 million qubits if your chip has, say 500 qubits? Well, you're going to need 2,000 of these chips. You need to network them. That creates additional complexities and issues with errors, with software complexity, with optical links, and so on and so on. So life is so much easier if you could just put a lot of qubits, thousands or maybe tens of thousands or hundreds of thousands of qubits on a single machine. So for all these reasons, room temperature operation, perfect qubits, parallel operations, flexible connectivity, and scaling, this is why, as you can tell, this is why I'm so excited about neutral atoms.
It sounds really exciting, and I'm keen to learn more. Maybe on the building blocks. Can you describe the audience what tweezers are and what do they do?
The tweezers capture the atoms and hold them in place, and then allow us to move them, to rearrange the atoms, and thus rearrange the connectivity, determine which qubit is going to interact with which qubit. But lasers really do everything for us, right? They trap the qubits, they cool the qubits, they make the qubits interact by changing the energy levels. Even when we, at the end of the calculation or at any point in the calculation where we want to measure, see, okay, well, you put the system in a certain quantum state, what is it? You basically shine light on these qubits that are in the in a certain state reflect the light. Qubits that are not in that state don't reflect the light. So you can basically, at the end, take a photo of these qubits and then see how many shiny dots you have and how many not shiny dots you have. And that's your measurement.
Is the benefit of that the state does not collapse, or am I now messing up things? So normally,
what I described in this particular case is if you shine light on for the purpose of measurement, then the state collapses. But you don't have to. By the way, you don't have to measure all qubits at once. So one of the amazing things in QuEra's architecture is the concept of zones. Let me take the classical analogy. If you think about a von Neumann architecture for classical CPU, you have a processing unit, and then you have memory. And what the calculation does, it basically takes data from memory, brings it into the registers, does something, and then put the data back. We have the same concept with our computer. We have a region where qubits can be very stable for a very long time. We can move them, as I described, shuttling them to an area where we shine lasers on them to make them operate, and then we can move them back, and then we can move some of them to a different area where we measure them. So you can sort of imagine these different parts of the factory, a memory section, an operating section, sometimes called an entanglement or processing section, and then a measurement region. And so that ability to move qubits around allows us many degrees of flexibility.
And on the lasers, are there different lasers for trapping or cooling and quantum gate operation, or are it similar? And what kind of lasers are it? Is it iridium phosphide, or are different lasers?
They're different lasers because you require different wavelengths. So if you want to transition an electron from one energy level to another energy level, you need to find a laser that is tuned to that energy gap. And if you want to make a different transition, or sometimes you make a transition with two steps, you take an atom from here to here and then from here to here. So that's two different lasers, one for each step. So yeah, we deploy multiple types of lasers for multiple uses. Yes.
I think we talked already a little bit about it, but can you summarize it maybe in 1 minute? Why can the qubits be exactly the same? Why is every atom? You said it's neutral. It's neutral atoms, but you do manipulate them to different states, and the manipulating to different states, does it not create differences among the qubits? So why is it that if you manipulate with lasers and bring them to a different state, why do they remain identical? Can you explain that part for me, because that is not yet clear?
They are right that they may be different atoms, maybe in different quantum states or different energy states, but they're still all rubidium atoms, right? We're not using lasers to tell rubidium into another element, right? And when you look at rubidium atoms, that would be fun if we could turn rubidium into gold, right?
No.
We want to do that. They're identical to begin with. They all have the same weight. They have the same size. The energy, the frequency that you need to use to transition an electron from one state to the other is exactly the same for all the atoms. Of course, over time, they may be in a different state. And this is in contrast, again, with manufactured. They're identical because they're natural. They're found in nature. If you were manufacturing qubits and say, oh, I manufactured qubit, this has a little bit more contamination. This wire is a little thicker. It's difficult to make. I mean, if you were to make coins, yeah, they would look similar, but not perfectly identical. So that's the difference sort of between manufactured parts and natural parts.
Okay, and that's clear. Thank you. Maybe the quantum gate operation, the entanglement and the logic. How do you do that?
We use the, I mentioned that briefly before, we use the Rydberg blockade. We basically take atoms, we bring them relatively close to each other, we shine lasers on them to bring them to high energy levels, and through that effect called the Rydberg blockade, that generates entanglement and Rydberg blockade in other quantum operations. So when we want to do 2-qubit operations, we employ a certain sequence of pulses. When we want to do single qubit operations, that's a different set of pulses. So for instance, we want to turn a qubit from 0 to 1, or from 1 to 0, or something else. So every operation basically involves bringing qubits to a certain area and executing a certain sequence of laser and sometimes other electromagnetic pulses on them.
And can you provide a little bit context on the steps that you do with the readout and the quantum measurement? How do you measure the quantum states?
We measure the quantum states by taking a photo of the atoms after we've shined light on them. Atoms, qubits in certain state reflect that light. Atoms in other states do not reflect that light. So you basically see almost like a starry night photo where you say, I see these dots that correspond to qubits in a certain state. And then if you run the same calculation again and again, because of the probabilistic nature of quantum, you might get slightly different results. So very often in quantum calculations, you run the same algorithmic steps again and again and again, multiple times, 100 times or 1,000 times, to get good statistics about what the ultimate measurement is.
And how do you do that? How do you make a picture of neutral atoms? There are
It's just a microscope and a camera.
a microscope and a camera. But do you need, so for example, I went with ASML to Zeiss in Germany, Oberkaufern. But it also depends on what kind of coatings you use or what lenses you use. Or is it is it really a standard camera, or is it, how does it work? What exactly?
Of course, I'm making it sound simple. When I said it's just a microscope, it's not a microscope that you just buy on Amazon. It's not a $50 digital camera. It's a special design of a set of lenses. Remember that the atoms are also very, very small, and the whole field, I mean, we spoke about 4 microns apart, right? So let's assume that I have 200 by 200 atoms, which would be a ton, right? Would be 40,000 atoms. That's still, 800 microns by 800 microns. So it's really tiny. So you really need very high magnification. And then you need a sensitive camera that can do this quickly, because if camera takes a lot of time, then that limits the number of calculations you can do at every second. So there's a lot of both science and engineering challenges behind it, but simplistically, it's just a microscope and a camera.
Thank you. I would love to learn more about the Microsoft camera, but maybe for another discussion. And then maybe the reconfiguration. How do you dynamically alter the geometry?
We reconfigure the connectivity by moving the qubits. Each qubit is trapped in a laser beam, in a sort of an optical tweezer. And if we move the tweezer, if we move it in the right way, then we can move the atom with it while maintaining the state. So, of course, you have to know what you're doing, right? It's almost like if you're driving a car in a fast turn, if you drive too fast, then the car is going to fly off the road and the car's not going to be there after the turn. So if you move the qubits in some crazy way, then you can obviously sort of shake them enough that they fly off the tweezers. But if you do them correctly, then by moving the tweezers, and moving the tweezers could be done in different ways. So for instance, you might have an array of tweezers and then use some either mechanical or something else to just move them all together. You could do that through a hologram. There are different ways to rearrange the tweezers. But basically, when you move the tweezers, the atoms move with them.
Are there good control measurement systems? Like
in
semiconductors, for example, you have KLA who's measuring the process. So if things are not going well, what kind of process do you have to systematically improve?
Yeah, so I think you bring up a good number of points. So first, you do need to, like everything else, you need to calibrate. So even when we spoke about laser pulses, how long do the laser pulses need to be? And what pulse comes first? And what's the delay between the pulses? The same with movement of the tweezers. How quickly do you move them? What's the best route to move them? For instance, you can't move them through other qubits, right? You don't want to create sort of collisions. How do you solve the traffic jams? So everything requires thought and calibration, but that's a lot of the sort of technical work that's going on in building these computers.